In the last few related rates problems, we've had only two things that were changing at the same time. And so it was just a matter of finding out how those two things related to each other. In this example, we're going to see that there are three things that are changing. So it's a little bit more complicated, but not significantly more complicated. Let's see how that changes things. Once again, I want you to pause the video before I go through the steps and see if you can do this and then use me to check your work rather than just watching me solve this problem. All right, so in this problem, we have, starting from an intersection of two long straight roads, a car starts traveling north at a constant rate of 20 miles per hour at noon. At 1 o'clock, another car starts traveling east at 30 miles per hour. And we want to know at what rate is the distance between the cars changing at 2 o'clock. So our first step in our related rates reference sheet is to make a drawing of the problem. All right, so the drawing I'm going to draw is I'm going to draw my intersection here. We've got a car that's going north. We've got a car that's going east. And we want to know about how the distance between those two cars is changing. And north and east are perpendicular to each other, so we can do that. All right, the second thing we want to do is we want to circle all the facts we know. So north at 20 miles per hour. We're going east at 30 miles per hour. And we've got something happening at noon, something happening at 1 o'clock, and something happening at 2 o'clock. So those are all of our key ideas that we want to make sure is expressed from our problems. Okay, and so let's come up with some variables and express these facts in mathematical and calculus notations. All right, so I will call this first car N for north because it's traveling north. And this one will be E for east because that's traveling east. And for the distance between the cars, you know what? I'm going to go ahead and call it D for distance. You can call it X. You can see why D is going to be a weird choice in a couple moments, but it's not that big a deal. You can use any letter you like. All right. So the first car is traveling north at 20 miles per hour. How do we want to express that in calculus notation? Well, we're talking about the change of this distance right here. So it's the derivative of north with respect to time, and that's equal to 20 miles per hour. All right. At 1 o'clock, another car is traveling east at 30 miles per hour. So that's the same idea. That's just dE dt is equal to 30. And we want to know at what rate the distance between the cars is changing. So we want to know dD dt. And that's a little weird using d as the derivative notation and also using it as a variable, but I don't think it's that complicated. If you're confused by this, then go ahead and call this x or something else. But I'm going to go ahead and say dD dt as talking about the derivative of distance with respect to time. All right. There are a couple other facts that we know. We've got our 20 miles per hour, our 30 miles per hour, and the thing that they want us to find. So at 2 o'clock, how far has the north car traveled? Well, it started going 20 miles per hour at noon. So at 2 o'clock, it's 2 hours later. So N is equal to 40 at this specific moment. And how far has the east car traveled at this moment? Well, it started traveling at 1 o'clock. So it's been traveling for 1 hour at 30 miles per hour. So E is equal to 30. Okay, so now the next step in the problem is to find some sort of relationship between all of these things that are changing. Okay, so how can we do that? Well, we've got north and east and distance, and these are the sides of a right triangle. So this is just, once again, like in our first problem, the relationship between all of these things is the Pythagorean theorem, that n squared plus e squared is equal to d squared. So our next problem is to differentiate this with respect to time. And it's going to be the same thing that we saw in the first problem again. That the derivative of n squared is 2n, and we need to add in the rate because that's with respect to time. The derivative of e squared with respect to time is 2e dE dt. And the derivative of distance squared is 2d dd dt. All right, and so we want to solve for dd dt, and we know almost all of these variables. We know what dn dt is. We know what dE dt is. We know what n is. We know what e is. The only thing is we don't know what d is. What's the distance between these two cars at 2 o'clock? Well, once again, we know that e is 30, we know that n is 40, and we know that this is a right triangle. So 30 squared plus 40 squared is equal to d squared. 900 plus 1600 is equal to d squared. D squared is equal to 2500. If you were doing that in your head and you're thinking, hey, I know about 3, 4, 5 right triangles, so this has got to be 30, 40, 50, then that is an awesome use of your time-saving techniques by recognizing that whenever we talk about right triangles, whenever we can, we like using numbers that make everything work out properly. So we know that d is equal to 50, so we can just plug this in and go to town. So 2n is 80 times dn dt is 20, plus 2e, which is 60, times dE dt, which is 30, is equal to 2d, which is 100, times dd dt. 80 times 20 is 1600. 30 times 60 is 1800, is equal to 100 dd dt. 1600 plus 1800 is 3400, is equal to 100 dd dt. And we cross out 2 zeros from both sides, and we get that dd dt is equal to 34. And what do you think our units are going to be? Well, all of these velocities have been measured in miles per hour. So at 2 o'clock, the distance is changing by 34 miles per hour. Does it make sense that this rate is positive looking at the problem? Yeah, because over time, these cars are going further and further away. So the distance between them is going to be increasing over time. And that's exactly what we measure by looking at a positive derivative. Okay, so that was an example of a related rates problem where we had 3 variables changing instead of just 2. But it was just a matter, once again, of finding a relation that combined all of the values. Sometimes you need to find more than one. Sometimes it's going to take a couple of equations to have everything pull together. But in each case, you're going to be able to solve for the rate you don't know based on all of the information you have about the static moment that you're interested in and all of the rates that you were told about in the original statement of the problem.